In the last video, we learned what asymptotic analysis is and why is it used. In this video, we learn about asymptotic notations, which is how we represent rate of growth of a function in comparison to some other function. There are three notations: O, omega, and theta, which can be further subclassified as big O and small o, big omega and small omega, and theta is just theta. Let there be two functions, t and f. Both of them has input size n. If tn is equal to big O of gn, then rate of growth of t is less than or equal to g, which is another way of saying that t will never take more time than g. So, rate of growth of t is less than or equal to g. If we use small o, tn is small of gn, this would mean that rate of growth of t is always less than g. Here they can be equal, here they can't be equal, which is another way of saying that t will take less time than g. Now the third one is if tn is big omega of gn. This would mean that rate of growth of t is greater than or equal to g, which is t will never take less time than g. Similarly, if tn is equal to small omega of gn, then rate of growth of t is always greater than rate of growth of g, which is t will take more time than g. And the last one, if tn is equal to theta of gn, then rate of growth of t is equal to g. T will take same time as g. Here what we are doing is we are giving upper bounds and lower bounds in terms of other function, making it free from lower order and constant terms, which is why we use asymptotic notations for asymptotic analysis. Now let's see an example. Let there are three functions, f1, f2, and f3. Growth rates be 2n, 4n, and n square. Time taken by them for various input points. N is equal to 1, there would be 2, 4, 1. For n is equal to 2, there would be 4, 8, and 4. For n is equal to 3, 6, 12. What we see between f1 and f2 is f1 is always half of f2. So f1 is half of f2. When a function can be written as a constant multiplication of other, then this would mean that the growth rate must be same. So f1 is theta of f2. Let's say that there are three functions, f1, f2, f3. The time complexity is 2n, 4n, and n square. If we plot the time taken by them at different points, we'll see that time taken by f2 is always twice of f1. When a function can be written as constant multiplication of other, then the growth rates must be same. So f1's growth rate is, we'll use theta since the growth rate is same as f2's growth rate. If there exists a constant greater than 0 such that f1 is c times f2, then growth rate of f1 is equal to f2. In f2 and f3, f2 is 4 times n and f3 is n times n. When n is greater than 4, at that point f3 will be more than f2. Beyond that point f3 will always be more than f2. Before that point f2 will be more. For every c greater than 0 such that f is greater than c dot g, then we can say that f is greater than g. For every c greater than 0 such that f is less than c dot g, then f is less than g. These are the cases of greater than and less than. For the cases of greater than equal to or less than equal to, what we can do is f less than equal to g is same as not of f greater than g, which is not of for every c greater than 0 such that f is greater than c dot g. This would become there exists c such that f is less than equal to g. For f greater than equal to g, we'll write not of f less than g, which would be not of for every c greater than 0 such that f less than c dot g, which would be there exists c such that f greater than g. We'll be using all these definitions in detail in the upcoming videos to explain what big O, big omega and theta exactly are.